Hi, I'm Siu On Chan. I will talk about how random CSPs fool hierarchies to joint work with Hyojun. Hierarchies are a class of local algorithms for solving constraint satisfaction problems. Consider the task of checking whether a graph is too colorable or not. A level D solution to the bounded width hierarchy consists of the following. To every small variable subset S, we look at the satisfying assignments to S. In this example here, S is this set of 3 variables, and there are 4 assignments that will satisfy all the bicoloring constraints on S. So to this subset S, we need to pick a non-empty collection of satisfying assignments to S. We have to assign this collection of satisfying assignments not just to this subset S, but to every subset S of size at most D. Now we have many collections of satisfying assignments across different subsets, and we have to ensure these collections are consistent in some way. The consistency constraint says the following. The collection we pick for a subset S, when projected to a subset T of S, agrees with the collection for T. There is also the linear programming hierarchy known as Shirley-Adams. This time, to every subset S, we assign a distribution of satisfying assignments to S. In this picture here, I'm showing you the probability mass function of a distribution of satisfying assignments. Again, we have similar consistency constraints, saying that the distribution we assign to S, when projected to T, agrees with the distribution on T. And this time the projection simply means the marginal. More recently, there is the affine integer programming hierarchy. In this hierarchy, to the local satisfying assignments of every subset S, we now assign an integer, so no longer a non-negative real number, and we require that the sum of the integers to every subset S equals 1. We also have similar consistency constraints. The ARP relaxation was introduced by Bregensick and Guruswamy, and Bartow and Boulin and Croce and Opreso. This ARP relaxation is stronger than Gaussian elimination and can solve all abelian linear equations. But it can also solve certain promised CSPs that are not linear equations. Previous works have shown that if your CSP satisfies some condition X, then the random instances of this CSP will have a solution in a hierarchy H. Barnabas, Giorgio, Megan, and Tusiani shows that if your CSP is pairwise uniform, then your CSP will have lower bound to the LP hierarchy. Pairwise uniform means that to every constraint of the CSP, there is a pairwise uniform distribution of satisfying assignments. Under the same condition, with Barak and Kothari, we show lower bounds to the STP hierarchy. And later on, Kothari, Mori, and O'Donnell and Wisma shows lower bound to CSP that are pairwise uniform. For the bounded width hierarchy, Astarius and Darmouth show lower bound for the approximate graph coloring problem. More recently, Seattle and Stevney shows lower bound to CSPs that they call aperiodic. Their goal was to show lower bounds to the approximate graph homomorphism problem, a problem generalizing approximate graph coloring. In this work, we show lower bounds for CSPs that are non-constraining. Don't worry about the meaning behind these names, but I will note that the lower bounds to the bundle width hierarchies are in increasing order of generality. For the AIP hierarchy, Seattle and Sydney shows lower bound to the approximate graph coloring problem. In a previous work with Siu Jin, we showed lower bounds to CSPs that we call tilewise AIP neutral. In this work, we showed lower bound for CSPs that are non-constraining and lax. In this case, there are 3 sufficient conditions for lower bounds for the AIP hierarchies, and these sufficient conditions are incomparable. To each of the hierarchy, a level D solution can be found in time roughly n to the d. So, a linear level lower bound, which is the case for most of the results on this slide, suggests that the CSP may require exponential time to solve. Rather than looking at these relaxations in isolation, one can combine them to get stronger algorithms. Brakensick, Guruswamy, Voshna, and Sivny introduced the basic LP plus AIP relaxation. A solution to this relaxation consists of 2 parts, the LP part and the AIP part. The 2 parts are related by this support restriction. The support restriction says that if an assignment gets the value 0 in the LP part, then the same assignment must also get the value 0 in the AIP part. A weakness of the LP relaxation is that it cannot solve linear equations. So having the AIP part fixes this weakness. These authors shows that the basic LP plus AIP relaxation solves every tractable CSP on a Boolean domain. And they further ask, if you turn this relaxation into a hierarchy, will it solve every tractable non-Boolean CSP? Recently, Damov and Opresold made a conjecture. Under their conjecture, an even simpler algorithm, BW plus AIP, already solves every tractable CSP. This BW plus AIP hierarchy is similar to LP plus AIP, except that everything about LP is replaced with BW. These questions are interesting because of the CSP algorithms independently by Bulatov and STOC. Both of these CSP algorithms are highly non-trivial combinations of BW and Gaussian elimination. So if the answers to these questions are yes, then we will get a simpler algorithm for CSP. With that in mind, it is of interest to show lower bound to the LP plus AIP hierarchy. By now, various lower bounds have been shown. The lower bound of Leichter and Peko is particularly interesting because they showed that certain tractable CSP cannot be solved by BW plus AIP or by LP plus AIP. So they give a negative answer to the questions on the previous slide. But BW plus AIP or LP plus AIP are not the strongest relaxations proposed in the literature. In the literature, there is also the cohomological consistency hierarchy of Ocon-Hill. This hierarchy is like BW plus AIP but stronger. There is also the constraint basic LP plus AIP relaxation by Seattle and Sivny. This relaxation is like LP plus AIP but stronger. In our work, we show the first lower bound to the cohomological consistency hierarchy. We also show the first lower bound to CBLP plus AIP. And our lower bound is to the basic relaxation as well as for the hierarchy. I should also mention that Leichter and Pagel also managed to show lower bound to the cohomological consistency hierarchy. An open question left open by all this work is whether these stronger hierarchies solve all tractable CSP. We prove our lower bounds by generalizing the concept of closure from previous works. The closure of a variable subset tells us the constraints we must look at when defining the local solution to this subset. Previous works used this concept to construct LP lower bound. Let's consider free XOR. We know that each free XOR constraint has a pairwise uniform distribution of satisfying assignments. BGMT consider the following distribution of assignments to a collection of constraints. To each constraint in the collection, we sample from the given pairwise uniform distribution of assignments independently. Some variables may be shared among different constraints, so we have to condition on getting the same value to these common variables. In this example here, we have two constraints in the collection. We also have this green variable subset, S. In other words, S consists of all the variables except x3. Of course, to define the local distribution to S, we have to consider constraints that are completely inside S. But sometimes we have to consider other constraints too. If we only consider constraints completely inside S, then we will be looking at no constraints. And then we will run into trouble later on if we want to extend the distribution to x3 as well. If the two constraints have different parities, then the two constraints imply an odd parity constraint to S. On the other hand, if the two constraints have the same parity, then they will imply an even parity constraint to S. So to correctly define the distribution to S, we have to consider the two constraints. Otherwise, the marginal distribution we define on S will be inconsistent with the marginal distribution we define on the two constraints. Sometimes, some constraints need not be included in the closure. In this example here, I'm adding an extra constraint, the orange constraint to the right. If you consider the distribution of assignments to the three constraints, and if you look at the marginal distribution to the green variables, then the marginal distribution will be the same as if the orange constraint is not there. As if you just sample from the uniform distribution to the two extra variables on the right. In this case, the orange constraint is invisible to the green variables because the orange constraint does not affect the marginal distribution to S. And therefore, the orange constraint needs not belong to the closure of S. So here comes the crucial definition from KMOW. We see that a constraint subset C prime is S closed if every constraint in this subset C prime shares at least three variables with S or with other constraints in C prime. Under this definition, the two black constraints are S closed. On the other hand, the orange constraint is not S closed. So, to correctly define the local distribution on S, we want to consider all the union of S-closed constraint subsets. This definition of closure of S is almost correct, except that you will be looking at too many constraints because the union of S-closed constraint subsets would essentially be all the constraints in the instance. And all the constraints in the instance will be unsatisfiable, so you won't be able to define a distribution of satisfying assignments to the closure. So KMOW instead work with a local version of this closure. They put an upper bound on the S-closed constraint subset C prime when you take the union. By using the expansion and sparsity property of the random instance, they can show that if the variable subset S is small, then the union of these S-closed constraint subsets C prime is also small. KMOW believes that their definition of closure is the right one. I agree with them, and that's why in our work, we will be working with their definition of closure as well as its generalization. We will introduce a generalization we call BW closure, where we change what it means for a variable subset C prime to be S-closed. We change the definition of S-closed, but otherwise we keep the definition of local closure the same. So at the end, we still get a new definition of closure that we call BW closure. We apply this BW closure to prove lower bounds for BW as well as ARP. We prove our BW lower bounds for null-constraining CSPs. A CSP is null-constraining if for every sufficiently long simple constraint path and for every pair of values assigned to its endpoints, those values can be extended to a satisfying assignment to the whole path. In this previous work with Molloy, we show resolution lower bound for null-constraining CSP. In fact, this resolution lower bound morally implies the BW lower bound in our new work. This is because resolution is a dynamic proof system, and BW hierarchy is morally the static version of resolution. In our new work, we make explicit the BW lower bound. We give a new definition for when a collection of constraints C prime to be not S-closed. A sufficient condition for it to be not S-closed is that it has a path of length L so that all the non-endpoints of the path are outside S, and these non-endpoints also do not belong to any other constraints in C prime. Of course, this definition here is meant to take advantage of the null-constraining property. It is not difficult to see that if a constraint collection C prime is not S-closed because it has such a path, then the set of satisfying assignments on these constraints, when projected to the variable subset S, will be the same as if the path is not there. So again, the path does not affect the projection to S. This property here looks exactly the same as the property that was used for proving LP lower bound, and that is why we are able to prove BW lower bound. In our work, when proving LP lower bound, we may have to work with this pairwise closure. When proving BW and ARP lower bound, we have to work with this BW closure. So our work also proposes a generalization of these two types of closures. We identify the common properties of these two types of closures to keep our proofs short and modular. ARP lower bounds are harder to prove because ARP solutions have no natural interpretation. So in our work, we construct the ARP solution recursively, making use of the null-constraining and lax properties. We see that a CSP is lax if for every constraint of the CSP and every variable of the constraint, there is an assignment to the remaining variables so that the assignment already satisfies the constraint, regardless of the value actually assigned to the particular variable. The following CSPs are easily seen to be null-constraining and lax. These include free set, free not all equal, hypergraph coloring with more variable per constraint than colors, as well as the rainbow coloring variant of this problem. So, our ARP lower bounds apply to these CSPs. A simple sufficient condition for lax is that the satisfying assignments of every constraint contain a Hamming of radius 1. For details of our ARP lower bounds, please see our paper. The following theme has emerged in our paper. If we know how to construct the hierarchy solution using closure, and we know how to construct the solution to another hierarchy using closure, then we can construct a hierarchy solution to the combined hierarchy, also using closure. It's like saying that if you know how to defeat two hierarchies separately using closure, then you can defeat their combined hierarchy for free. We know that pairwise uniform CSPs fools LP using closure, null-constrained and lax CSPs fool ARP using closure, and that's why pairwise uniform and null-constrained and lax CSPs fools LP plus ARP. And because pairwise uniform implies null-constrained, so I don't have to state it. I hope our work convinces you that closure is a versatile technique for proving hierarchy lower bounds. Thank you for listening.